Assalamu alaikum wa rahmatullahi wa barakatuhu. So in this series of videos we are looking at the induction motor, and so in this video still we will continue with our topic of induction motor. As in the previous videos we have seen that how the induction motor works, and the most important phenomena of the induction motor, which is the slip, and that slip is actually the difference between the speed, synchronous speed of the rotating magnetic field and the mechanical speed of the rotor itself. So that is the relative motion that actually produces the torque in the induction in the induction motor, and that is actually very much required. Now we will continue with the equivalent circuit of an induction motor. So an induction motor relies for its operation on the induction voltages and currents in its rotor circuit from the stator circuit. So the induction of which is known as the transformation. So the induction of voltages and currents in the rotor circuit of an induction motor is essentially a transformer operation. So the equivalent circuit of an induction motor will turn out to be very similar to the equivalent circuit of the transformer. So an induction motor is called singly excited machine as opposed to the doubly excited synchronous machines, because we do not supply the DC to the rotor, since power is supplied only to the stator circuit here. So the induction motor does not have an independent field circuit. Its model will not contain an internal voltage source such as the internal generated voltage EA as in the synchronous machine. So then this is how it will look like. We have this R1 JX1, and this is our stator, and this is our excitation branch RC JXM, and then we have this A effective, and obviously we have the effective turns ratio because in the stator, mostly if we can count the number of turns, but if we have the cage rotor, so that they are the bars and we cannot actually count the number of turns there, so that's why you use the terminology effective. And there is no EA here, but we just have the JXR and rotor resistance on the rotor circuit side. So this is the flux, the MMF, and the flux curve will be different from the transformer than the induction motor. So the stator resistance R1, the stator leakage resistance reactance X1, air gap in the induction motor, which greatly increases the reluctance of the flux path and therefore reduces the coupling between primary and secondary. So higher reluctance means the higher magnetizing current is required to obtain a given flux. So the primary internal stator voltage E1 is coupled to the secondary ER by an ideal transformer with an effective turns ratio A effective. So the effective turns ratio is fairly easy to determine for a wound rotor motor, but it's basically the ratio of the conductance per phase on the stator to the conductors per phase on the rotor, modified by any pitch and distribution factor. So it is rather difficult in the cage rotor motor, because there are no distinct windings on the cage rotor. So in either case there is an effective turns ratio for the rotor. So the voltage ER produced in the rotor in turn produces a current flow in the shorted rotor or secondary circuit of the machine. So here it is shown as a short circuited, and because of this voltage induced ER, there will be the current flowing into the rotor circuit. So the primary impedances of the magnetizing current of the induction motor are very similar to the corresponding components in the transformer equivalent circuit. So this is how we can see that this is the magnetization branch, and this is the winding resistance and the leakage flux of the stator. So an induction motor equivalent circuit differs from a transformer equivalent circuit primarily in the effects of varying rotor frequency. So the only difference that comes when we have different rotor frequency, because in the transformer we had the same frequency on the primary and secondary sides. So the rotor voltage ER and the rotor impedance R and JXR. So In an induction motor, when the voltage is applied to the stator windings, a voltage induced in the rotor windings of the machine. So greater the relative motion between the rotor and the stator magnetic fields, the greater the resulting rotor voltage and rotor frequency. So the largest relative motion occurs when the rotor is stationary, called the locked rotor or blocked rotor condition. So the largest voltage and rotor frequency are induced in the rotor at that condition. So this is the condition that obviously we might have observed sometimes, that when the motor burns, so what happens that the by some means or by the problems of the bearings, means usually at our homes, that we use the small motors, and we don't actually we usually do not service them regularly, so that sometimes the bearings get the rust and they get stuck, and that condition occurs, and at that time we have seen that the maximum current flows, and that maximum currents will actually produce a lot of heat, and that will in return burns the stator windings. So the smallest voltage, 0 volt and 0 hertz frequency, occurs when the rotor moves at synchronous speed as the stator magnetic field, resulting in no relative motion. So the magnitude and frequency of the voltage induced in the rotor at any speed between the extremes is directly proportional to the slip of the rotor. So we will make some assumptions, that we call that the maximum voltage that is induced in the rotor at the locked rotor rotation as ER0. So this sub-zero means that it is locked rotor, no speed. And at any other speed, the induced voltage in the rotor ER is S times ER0. Similarly, we know that FRE is equal to SFE. So this voltage is induced in the rotor containing both resistance and reactance. So the rotor resistance is a constant except for the skin effect independent of slip. So the rotor reactance is affected by slip. So the reactance of an induction motor depends on the inductance of the rotor LR and frequency of the voltage and current in the rotor. So we can say that XR is equal to omega RELR, which is equal to 2 pi f RELR, or we can write it in terms of here SFSE, or we can take out this S here, and 2 pi FSE LR, which is same as S times XR0. Okay, so we can have this reactance at any frequency, which will be directly proportional to the slip. So this is, here we can see the rotor circuit model here. So here we have the ER, which is SR ER0 at any frequency. Similarly, JXR is equal to JS XR0. RR will be same. And if we just take out the slip common from here, so that is how it will look like. So here in the equation form, here we can see here as ER is equal to RR by JXR and ER0. So actually this is I'll make a small correction here. So this is S times ER0 by R JSXR 0. So if we take this S common from here, from the top and from the bottom, so it will be ER0, here it will be RR by S, so it will cancel out. So that's why here we will get RR by S. So, and this will be simply JXR0 and ER0. So here we can see that model of all the rotor effects due to varying rotor speed is as being caused by varying impedance supplied with the power from a constant voltage source ER0. So ZR equivalent will be then RR by S plus JXR0. So rotor voltage is constant here, ER0, and the rotor impedance ZR equivalent contains the effects of the varying rotor slip. So at the low slips, the resistance RR by S will be higher, because this is in denominator S, and comparatively to this XR0. So the rotor resistance predominates of the rotor current varies in linearly with slip. So at high slips, RR by S, which will be higher, so this term will be smaller, will be comparatively less than XR0, and the rotor current approaches a steady state. So here we can also reduce the effect of the effective turns ratio. So these are the basic relations that we know for the transformer, that Vp is equal to A times Vs and Ip is equal to Is over A, and Zs prime is equal to A square Zs. So similarly here we will have E1 will be A effective ER0 and I2 is equal to IR by effective, Z2 will be A square effective RR by S by JXR0. So that's why we have transformed this rotor model to the primary side or on the stator side, so that we can have this transformed rotor parameters. So I hope you have understood this topic, because this is quite similar to the transformer equivalent circuit. So we don't have to go in depth to define each and every component that we have in this model here, just like R1, JX1, RCXM. So we have just assumed that you know these all basic things how we have reached up here. So we just modeled it in terms to show the effect of the motor effects, that what happens if this model is used for the induction motor. So we have just mostly considered all those things which are just necessary to describe the induction motor model. So I hope you have understood, and still if you have any questions, please feel free to ask. Assalamu alaikum wa rahmatullahi wa barakatuh.